Okay, we're continuing with antidifferentiation, or taking the integral of a function. The first ones that we did were very simple. It's basically a power rule, very straightforward, some memorization that goes along with it, and just some practice, and we'll continue to practice them. This antidifferentiation of a composite function takes a little bit more time to get used to. And I'll show you some examples here, and then I will show you some examples in a live lesson. So what we're looking for is it's basically the chain rule. So the chain rule said f of g of x, if I want to take a derivative of that, I had to take the derivative of the inside times the derivative of the outside. And so now what we're doing is we're working backwards. So we have to recognize the derivative of an inside function. And once you get to recognize what you need to differentiate, which is the function and which is the inside of the function, then it makes it a little bit easier to do these. So this is the first example, as I have the integral of x squared plus 1 squared multiplied by 2x dx. I cannot take and integrate this because of this squared here. I could if I expanded all this. But a lot of times when you're using a chain rule, you might have a power that's a lot larger than 2. And so expanding it just becomes cumbersome and not worth the effort. So the inside function is this x squared plus 1. So I'm going to let u equals x squared plus 1. So du, the derivative of u with respect to x, is going to be 2x dx. That's important because I've got this 2x dx, and that's going to be replaced with du. This u, this x squared plus 1, is going to be replaced with this u. So we're going to integrate u squared du. Now it becomes a much simpler problem. But recognizing what has to be u, what has to be du, and the manipulation of them is really the art form behind this. So now I can easily integrate u squared. So I have to add 1 to the exponent and divide. And I have to remember to add c. And on the assignment that I was just grading, you guys were doing fantastic at remembering c. But then I have to go back and replace u with x squared plus 1. Well, it's not hard. I have x squared plus 1 cubed over 3 plus c. If you would rather write it as 1/3 x squared plus 1 cubed plus c, that's fine too. Either one of these is acceptable. My next example is similar to this, and I could expand this fairly easily and get 1 minus 6x plus 9x squared dx. So then when I integrate that, I'd have x over 1 minus 6x squared over 2 plus 9x cubed over 3 plus c. And that's not difficult. But I'm going to go ahead and show you what happens with U substitution. So U is going to equal the inside function. So this 1 minus 3x. So du is going to equal negative 3 dx. And this is where different teachers show this different ways. Different students pick up on this in different ways. I notice that I have a dx here. I don't have a -3. So I'm going to solve this for dx. And I get du over -3 equals dx. So then when I replace this, u is 1 minus 3x, so I have the integral of u squared. Replace dx with du over -3. And then I tend to just clean it up. This is saying -1/3 u squared du. So -1/3, I'm going to multiply that by u cubed over 3 plus c. Replace the u cubed with this 1 minus 3x. Let's do it this way. 1 minus 3x cubed over 3. So I get -1/9. Oops, I forgot the plus c. -1/9 1 minus 3x cubed. And this statement and this statement are equivalent. I would just have to get a lot of work to get from here to here. This is, for most people, they would rather do this U substitution to get to this answer. But there's nothing wrong with up at this answer. Okay, so then my next example, now you can see the next example, I have an exponent of 5 here. So there's no way I would want to write 2x cubed minus 1 5 times and multiply it. I would make a mistake at one point. So I would never do that. So I would recognize this as U substitution. So I'm going to let U equal 2x cubed minus 1. That's my inside function. So du is going to be equal to 6x squared dx. And I need to recognize I have x squared dx here. I have x squared dx there. So that means I'm going to take and divide by 6. So then my integral becomes u to the 5th power du over 6. I'm just going to write this as 1/6 integral of u to the 5th du. U to the 5th, when I integrate it, is going to be u to the 6th divided by 6 plus c. So I'm going to bring that 6 out here and multiply. I get 1 over 36. Replace u with this 2x cubed minus 1 to the 6th power, and then plus c. So the polynomials are fairly straightforward. When we start getting into more complicated one, it's not as easy to see. So here's an example with the square root. And I'm just going to rewrite this as x 3 minus 4x squared to the -1/2 dx. Then it's easier for me to see what I need to substitute. So u is going to equal 3 minus 4x squared. So du is going to equal -8x dx. Well, even though they're separated, I've got an x and I have a dx here. So I want this x dx. So I'm going to divide by -8. So my integral becomes 3 minus 4x squared is replaced with u. So I have u to the -1/2. And then x dx is replaced with this du divided by -8. I'll rewrite it as -1/8 integral u to the -1/2 du. -1/8. U to the -1/2, add 1 to that, I get a u to the +1/2. Divide by 1/2. And I'm going to change that because that bothers me. Add C. When I divide by 1/2, I'm multiplying by 2. So what's going to happen, when I multiply by 2, I have negative 2 over 8, u to the 1/2 plus c. So it gets written as equal to negative 1/4 u to the 1/2. I can leave it as 1/2 power, or I can do a square root. I'm just going to do a square root. And there's my answer. So be very careful. When you first do these, make sure you identify u correctly. And then when you do identify u, and it's usually the more complicated term or something that's inside something else, then make sure you're very careful at calculating what du is.